Mark Elliott. I am the Chief Operating Officer of Europa Science Limited, and we are the publishers of Electro-Optics. Welcome to everybody watching to one of our Photonics 100 webcast series. Today's topic is on greenhouse gas sensing, where there have been some fantastic advancements in this space, but still plenty of challenges left to overcome. We have two speakers today. Unfortunately, the third speaker, Shankar, who's the CEO of Earth Eye Space, has had to pull out at the last minute. He sends his apologies. If there's anything you wanted to contact him about or to get his views on, please just get in contact with us at Electro-Optics and I'll pass on your questions. So without further ado, I'm going to introduce our two brilliant panelists that we do have today. First of all, Anton Leemhuis, who is the Business Director, Earth Observation at TNO. He is heading up this activity for the Netherlands Organization for Applied Scientific Research. He's working on the Tango project with the European Space Agency, and he sits on the board of the Dutch research consortium Clear Air. Welcome, Anton. Very pleased to have you with us. And I'd also like to introduce Tim Olsen, who is the VP Technology and Engineering from our partners on this webcast, Omega Optical. Tim's had a long and varied career, starting off in the US Army, and has been at Omega since 2018, and they've done some really interesting work. So really pleased to have them both here. We're going to run for about an hour. There's an opportunity for anybody watching this live to send in some questions, and I'm very pleased to say we've already got some that have just come in just now. So we will come to those during the discussion. So please bear with us. We'll try and get through as many of the questions that are coming in as we can. And I wanted to start off the discussion with a fairly broad-based starting point, which is about the biggest challenges currently involved in sensing and measuring greenhouse gases using, of course, photonics technologies. It's a broad topic, so let's just see where it takes us. Anton, where would you kind of define where we're at with those challenges? What are they and what are we doing about them?
I think the biggest overarching challenges is that there's not so much sensing going on. So what we know about emissions is mostly based on statistical data. And in some cases, we know from measurements that are made that those estimates are really accurate. But in other cases, we see that they are not very accurate, both in terms of output of emissions, but also in terms of location. Sometimes we don't even know where emissions go up in the air. So state of the art is, I would say, we need more of that sensing.
Is that kind of view shared more widely around the organizations that you're working with? Is there a consistency about the view that we need more sensing? I mean, you know, is it something that everybody is focused on in the right way?
No, it's not a consistent image. I think there is a consistent appreciation that sensing is important, but it really differs per application whether our customers and partners feel it is needed. And I think there's two sides of that story. On the one hand, people say, look, legislation ultimately determines what needs to be sensed and what not. And legislation for many cases, especially in the greenhouse gas arena, don't prescribe measurements to be used. On the other hand, people say, well, there is this big uncertainty about greenhouse gases. Look at methane, it's going up rapidly, but where is it coming from? Big fundamental questions remain, and people do acknowledge, by and large, that sensing is an essential part of solving that mystery. So I think on the scientific side, it's undebated. On the policy side, it is appreciated, but not turned into legislation in many cases. Some important exceptions there.
Okay, that's interesting. That's interesting. I think almost certainly, well, somebody's got an echo on their thing. If you could mute your microphone when you're not speaking, that'd be helpful. Thank you. Yeah, so I mean, obviously, sometimes legislation catches up with kind of, I suppose, expert opinion and public opinion. Tim, from your perspective, I mean, what do you think the biggest challenges are, and what should therefore the priorities be, and what is being dealt with?
Well, as at Omega Optical, we're more focused on the sensing side than the policy or any of that stuff. I'm an optical designer, but we're seeing a growth from all our sensing companies, and we're seeing significant growth in gas sensing type measurements. That's driving us to manufacture and develop new specific coatings for inside the instrumentation, and that's really on the other side where I live, on the instrumentation side. So as far as the policy and the legislation, that's way above my pay grade.
Fair enough. And in terms of the type of solutions that you're being asked to kind of come up with, is there a consistency or a kind of an area of focus that kind of predominates?
There's it's survivability of the testing cells when you're testing, depending on the concentration of the gases that you're measuring, improvement in the instruments running longer without maintenance, etc. Things like changing out. We specialize in FTIR analysis, so changing out the helium neon laser to a VCSEL laser or a semiconductor laser, just so that there's more consistency and the instrument operates over a longer period of time. Then there's the coating technology that you need to apply to the optics so that the degradation of the gas cell and the instrument itself over time. And those are the things that we see at a more of a micro level in our business. But what we do see is the growth of our business. I've been here for 6 years, and we've grown as much as 60% in over the last 6 years.
Right. And has the growth been steady, or has there been a big incline in the last sort of year or two?
Well, it's a little skewed. It's a little skewed because the FTIR instruments are also used for other things. But our gas sensing customers, I would say, have been a steady growth with the deployment of more instruments around the world. And the manufacturers are all over the world looking at different things. So that's what we see.
And just while we're on this sort of subject of the actual kind of core sensing, I mean, are there differences to consider about sensing levels for different gases? So obviously thinking about some of the more obvious ones, carbon dioxide, methane, nitrous oxide, etc. What is the typical range of kind of approach that you need to take with those kind of gas sensing challenges?
I mean, as far as we're concerned, as a component manufacturer and not basically an instrument builder, we're looking at there's certain techniques that I see the instrument builders are using. They're using aspherical optics to improve signal to noise ratio. They're using a combination of filter technology to separate out bands to create a higher signal to noise ratio, just so they can get lower and lower concentrations measured, down to parts per trillion. You can get nowadays.
It sounds to me like it's like a lot of kind of industry and kind of scaled up applications. It's all about reliability, scale, cost, all the kind of things you would expect and things. And coming back to you, Anton, on this point, I mean, is there a kind of an industry expectation about solutions of this type? I mean, do people that you're talking to, or indeed, Tim, possibly even from your side, customers that you're being approached by, are they coming in with a base understanding of what's available, what to expect, or is it very disparate at the moment? How consolidated has it become? Anton, I'll start with you, and then Tim, maybe you could answer.
Yeah, so sensing is a broad domain. There are many different levels, if you will, to measure greenhouse gases. You can measure them, let's say, in the pipe or in the chimney stack. You can measure them downwind if you cannot access the stack. You can measure them using aircraft, remote sensing techniques. You can measure them using satellites. And all of them have their specific pros and cons. And I think what I see a lot with customers is that they are trying to figure out which of these observation strategies work best for their needs. Now, obviously, all those observation strategies require different instruments and different components. The arena where TNO is very active is remote sensing and space-based measurements using spectrometers. It's a very different industry than developing sensors that go into chimney stacks to do in situ measurements, and they have different applications. So but basically I see 4 different use cases with 4 quite different industries involved.
Okay. And is there and in terms of sort of standardization and possibly legislation, which we've already discussed is a bit behind the curve, is there a kind of consistency of approach in those 4 areas, or not really from your perspective?
Not what I see, but I'm mostly focusing on the remote sensing side of things. What you what you see is that the biggest application that I'm involved in and that I hear customers about is verification. So I think it's very clear that statistical data is the main backbone of greenhouse gas policy, and policy is what drives us in terms of reduction targets, of why we want to measure it. And for this verification, there's no standards yet. And I think they will have to be developed in time for measurements. For statistical reporting, there are many standards.
Yeah. Okay, that's an interesting picture there. Would you kind of agree? What that you've seen the same kind of slightly disparate approach to this sort of this kind of implementation? Tim?
Oh, to me, I'm sorry, I didn't know you were talking to me. No, most of our customers are, they're focused on growing their business, right? So, but they're focused on a lot of them are focused on stack monitoring. Then they are getting into remote sensing, being able to put things into harsh environments. They're ruggedizing their instruments and looking at things remotely. But and there is a trend towards smaller and smaller optics, things like that, so that they can put these ruggedized small packages many places and monitor the emissions.
Okay, that's good to know. Well, I want to talk a bit about equipment in a moment, but this might be a good point to kind of answer, if we can, one of the questions that's come in, which is about how to integrate greenhouse gas sensing technologies into existing industrial processes. Are there any kind of common, shortcuts, good advice things, or and if not, what's stopping that being the case? I appreciate there are probably thousands of use cases in reality, but are there any kind of words of wisdom that you could share about how to make that as easy as possible? Anton, I'll go with you first, if I may.
Yeah, no, maybe building a bit on what I stated in the previous. I think a really important step to integrate this in industrial processes is clear specifications and requirements from governments that they want to see this measurement data. Technical innovation has come a long way, and there's a lot more possible today than 5 years ago or 10 years ago. So it would be great if measurement practices become part of, let's say, IPCC guidebooks. Another important initiative is the OGMP, the industry standard that is being set by oil and gas companies for methane measurements. They see the potential of measurements, but it's not prescribed often. I think this is an excellent venue where it can be pursued more aggressively, and also here standards can be set. So we get intercomparable data, and because I think that's really important. We know instruments can help us with measurements, but ultimately the data needs to be able to use, and therefore it needs to be intercalibrated, compared, etc. I think these are some important steps that the industry and the government can make.
Okay, yeah, I mean, the importance of the right data used the right way seems to be a kind of continual theme across anything to do with, well, everything really, I guess. You know, Tim, you're at the sharp end of dealing with customers who are coming to you with a need to find a solution to something they're trying to fix. Are there any, particularly thinking about industrial processes in particular, I mean, are there any particular things that customers should and shouldn't do? You know, is it about planning? Is it about getting the data clear in their heads before they start? You know, what do you see customers doing well and not so well?
Once again, we're a little further upstream, and we're just responding to what they need. So it's all about making the instrument more sensitive. But you know, we don't get involved in the data aspect of it. But I can see where the standardization of the data and the algorithms that are used for the data are all adhering to some type of standard throughout the industry. And it just seems like, from what Anton's saying, is that that's not there. And I think that would be really important. And then we can make the instruments do what they need to do to adhere to those standards. But it's to me, from my experience, on that end, my little experience on that end, is that the data and the libraries, all those things, and the algorithms that they're going to use need to be standardized so that governments can improve the policy.
Yep. So anybody watching from government, take note. We look for kind of you to take a bit of a lead on this, and we will be watching carefully. Okay, I want to move on to the equipment now, if you don't mind. I'm interested, moving away from perhaps some of the industrial kind of processing stuff that we were just talking about, thinking about the researching levels of greenhouse gases in the atmosphere and ocean. And I'm wondering what kind of sensors, cameras, and spectrometers are proving particularly valuable in terms of good researching levels in this space. Tim, any particular tips or ones that you think are doing particularly well, or perhaps needing or have had some significant advancement of late?
Once again, we live in the FTIR world, and the FTIR has been using to measure these gases for a long period of time. What's nice about these gases is that they're in the mid-wave region of the infrared spectrum. You can use, you don't need a hygroscopic beam splitter to do that. Developing, better optics inside the multipass gas cells, coatings to give better reflectivities, protected gold type coatings that, give you higher reflectivity and, increase your signal to noise. And then you can couple those with, if you're looking with, say, optical filters, which is the other side of our business makes optical filters that can get you higher signal to noise ratio. It's all about getting lower, detection.
Okay, got it. And Anton, from your side of things, are you getting involved in those kind of choices, or are you dealing more with the output once they're in place?
Oh, absolutely. Yeah. So TNO is a developer of instruments. So as I mentioned, we mostly work on remote sensing instruments, but we also have a group working on ground-based instrumentation, mostly for doing instrument development that measures emissions downwind from facilities. Yeah, and I fully recognize what has been said. So the FTIR is, I think, on ground-based activities important. In remote sensing and from space, it's a little bit a different approach. Here, the spectrometers are still the dominant workhorses. So I think most remote sensing data that you will see today of greenhouse gases is of spectrometers. Big exception is the Canadian company GSAT, who has done excellent work with interferometers. And I think this is for over a decade already really an area of research in remote sensing. So how can we benefit more from interferometer technology? In terms of signal to noise, there's clear advantages of it. And the reason why people do stick to the spectrometers is that they give you a a lot of data also outside the frequency ranges that you strictly speaking need to measure the gas. And if you measure something from 1 or 2 kilometers up in an aircraft or 500 kilometers remotely from space, you need to remove a lot of noise from your measurement. And all that extra data is really helpful to clean up the measurements, to do corrections. So this is why the spectrometer is still widely used in remote sensing. So we've seen a lot of improvements in spectrometer technologies using especially freeform mirrors, so reflective optics, to really increase the efficiency and the SNR of instruments and to make them smaller yet more performing.
And do you see those technologies being reliable and the core of the activity for a long time? Do you see anything kind of nudging into the edges of what they do?
Yeah, no, so I see the interferometer becoming more and more important. But ultimately, my view is that in remote sensing, they both the spectrometer still has a very long life ahead of itself. And I think you see that with the need to boost signal-to-noise ratios, I think you may even see that they will be used alongside each other. Because they are very different animals. They both have very strong pros and cons. And remote sensing is a fairly expensive way of measuring things in terms of making the instrument. But its cover is enormous. So the cost per measurement is not that high, actually. It really competes with ground-based measurement. Because you only have to make one instrument, it's actually quite attractive to kind of combine those two measurement technologies. So that's one direction. The other is that you see miniaturization, and you see this whole constellation way of thinking, where people will build, instead of one big expensive satellite, they will build smaller ones that have a shorter life expectancy, and their rate of innovation goes really up, because that is traditionally hindering remote sensing from space.
Okay, Tim, I saw you nodding to much of that.
I mean, those are all the things our customers talk about. We supply gratings for spectrometers and interferometer components. So those are all the core technologies that are being deployed right now. And we have FTIRs in space doing remote sensing and diffractive optics up in space. So I just everything Anton is saying is what we hear.
That's good. Nice, consistent message. Sometimes it's good when people massively disagree, but stuff, there's a consistency of evidence that kind of avoids that. So nothing wrong with that at all. I just wanted to also talk on the sort of perhaps a slightly more technical end of this. What particular specifications, and I'm thinking specifically of things like spectroscopy, wavelength, concentration range, sample rates, are involved with, particularly as we were talking about it, the atmosphere and the ocean, greenhouse gas sensing? Are there kind of particular kind of commonalities? I'm guessing there probably are. Tim, that's what you're seeing a bit
Well, yeah. The optics inside these instruments are all centered in the mid-wave infrared.
Yeah.
So but as opposed to some of the broader spectrum FTIRs that go from 2 microns up to 25 microns, and we have optics that go out to 50 microns using cesium iodide beam splitters versus zinc selenide. But when you get to the using the zinc selenide beam splitters, you can narrow your band down, and you get better signal to noise with that, and more effectively shorter acquisition times.
Okay.
You're not scanning along a broad band.
Okay. And Anton, you'd agree with that? Anything particularly you want to add about this?
No, yeah. So I agree. I think one of the you mentioned from 2 micron on. We see also still that's I think roughly consisting what you said. So the 1.6 micron area, very interesting for remote sensing. So 1.6, 2.3 microns is where we see most instruments being focused on. I think one of the key debates in the instrument making industry business is now what spectral resolution you should aim for, and you have different schools. I'm from the Netherlands, and we build a lot of instruments on this in the Netherlands. So I always call this the Dutch school, but that's maybe a bit chauvinistic what I'm doing here. But these are with a very fine spatial resolution of 1 nanometer or less. Whereas others say, no, don't take such a fine spectral resolution. Take a much cruder one, 5-10 nanometers is enough, because you get a much stronger signal then. And that's a little bit the debate. That has to do mostly with the end usage. So scientists always like very high resolution measurements because they can resolve the spectra in a very nice way. They also want high signals. So then, which is the optimum? I think nobody has the answer. But I see two different families of instruments developing. So very fine spectral resolution versus a bit more cruder.
Okay, Tim, would you agree with that?
And then you look at the trade-offs. With data acquisition time and processing and all the things that come with those two different decisions, right? You want finer resolution, you have longer scans and an interferometer. But you get more signal with a more coarse resolution. That's up to the scientists, monitoring the gas.
And tell me, when you're kind of working on a project, like this, do you find that what you're asked for changes when you're going into sort of like the implementation stage? I'm wondering if people come into these kind of conversations with you, I'm thinking particularly Tim, perhaps to kick off, with a clear view on what they feel they need, and then that view changes over time, and I'm thinking particularly around the actual kind of measurement quotas that they're after. I mean, does that tend to shift, or is that usually the same at the beginning of a project and at the end?
By the time it gets down to our level, it seems the customer knows what they're doing on the end of resolution, and they're just specifying components that they need to achieve that. That's the end. That's the end I live on. So we get very specific specifications for our coding or our optics, and so by the time it reaches us, they know what type of instrument they want to build.
And then Anton, from your perspective, you're working perhaps a little bit earlier in the chain sometimes. Does that shift over time during the development process?
Absolutely. So we work in the chain we use remote sensing data and ground-based sensing data to measure emissions. We develop instruments, we develop new missions around it, and then we're also part of setting up the supply chains with the suppliers. So we are active basically through this whole value chain, and lots of trade-offs are made in the beginning. So in the beginning, this can go in many directions. And in particular for remote sensing, because the instruments themselves are fairly capital intensive to make, the requirements shift. But at some point they are frozen because there's no tinkering around anymore. I mean, these are expensive developments, and you cannot just change it anymore. So I see a very rigorous process to transform policy and science requirements into instrument requirements and then component specifications.
Okay. Now, I hear this sometimes, that the best laid plans, meticulously kind of researched project works seamlessly from, implement all the way through to implementation. When it hits the ground, when it actually has to work on in the field, if you like, it can sometimes go wrong. And I'm now wondering about, what happens when it, is being deployed in real life, so to speak. I'm wondering about, the deployment of the equipment involved in the atmosphere measurements and possibly ocean measurements in particular. What do field workers need to be on top of? What tends to go wrong, if anything at all, once it's actually hit real life scenarios? There's a difference, isn't there, between researching in a project in a kind of a controlled environment to the real world. What are there any common issues around this, or things that people should or shouldn't do? Anton, I'll go back to you if I may, just quickly on that one.
Yeah, sure. Well, so it depends really on which part of the measurement chain you are. So I think in the downstream side, when we look at remote sensing instruments, I see, that's not something that goes wrong, but I think it's often not maybe appreciated. There's lots of data that is not being used. There is terabytes of greenhouse gas data being measured every day by satellite instruments. So yeah, please use it. Yeah, it's because if you don't use it, it doesn't have an impact. Calibration is always very important. I see lots of initiatives to deploy remote sensing instruments in a very quick fashion, which is admirable, but it needs to be precise. So calibration and verification and validation measurements of these instruments are very important. Instruments in themselves in remote sensing, often, especially in space, you cannot do too much about it anymore. So a good calibration on ground is really important, and this is where you solve your issues. I'm proud to say that even though for decades DNO has developed instruments that fly on NASA and ESA satellites, they all work. So that's a good news. That's really prepare things well. That's really really important. It's not so difficult to build a sensor. It's really difficult to make sure it's really trustworthy.
Yeah,
and my comment on that would be if it's a problem on my end, then there was some very bad decisions made
earlier on. Yeah.
If
they're coming to me to fix something, coming to us to fix something. There was decisions made that because we're far upstream. But anyway, yes. I can see that, right? Most of the time we're at the beginning, and this is what we need the coding to do. This is what we need the optics to do, etc. So
yeah. And tell me, Tim, do you get any exposure to that end of road process, kind of implementation? And if you don't, would that be useful for you as an organization if clients were kind of working, involving you all the way through the project?
Once again, we're optical people, so it'd be great to see it, and I have seen them work. But when you start talking about the data and how they process the data and how they evaluate the data, that's way from where our team plays.
Yes, yeah.
Our team is helping the instrument makers, helping the people put the beam splitter in space and those type of things. But and then we obviously working with our customers with the trade-offs that come with engineering an instrument.
We did an interesting project. Sorry to jump into this, but I just get too excited by this. It's traditionally I see this really strong division where the flow down of requirements from end users leads to trade-offs, the mission level design, instrument level design, components, etc. It's a very rigorous approach, but also very slow. What we've done in the Netherlands, we've developed the next generation greenhouse satellite mission. And the whole idea is to do that faster. So instead of the 10, 15 years it normally takes, the idea is to do it in 5. That's 3 times faster. And we do that by having an integrated team where the optical people and the scientists and the spacecraft people work together in one team. And that has been quite an innovative experience that worked really well because you shortcut so many I will say it's overheads and miscommunications, lost opportunities because you don't know what is really possible. Has been tremendously valuable to do that in an integrated fashion. But it does require you to learn each other's language because the scientists, the spacecraft people, everybody speaks a different language. But I think there's a lot of potential to gain more performance working in an integrated way.
Okay, is there a research paper done on that, Anton, or is there a kind of report summary that that you don't?
No.
I don't need. No.
About the results, yes, but not on the process. You give me an idea. Maybe we should write that.
Okay. Yeah. No. Absolutely.
The project is called Tango.
Okay. Tango. Yeah. Okay.
So the Tango mission of ESA is there's papers on that, so you can find these. But the way of working for future publications.
Okay, well, there we are. There's an outcome we weren't expecting from the webcast. We're going to transform the way some bits of the photonics industry work. That would be good. Tim, you're up for that, yes?
That'd be great. I mean, I think integrating everybody always is a better solution, so everybody understands what's going on. When you're at a component level or a subsystem level, knowing what the overall outcome needs to be, and getting even without being the expert in data scientists or analytics, you get a feel, and then you can come at it from your perspective. So that would be excellent if our customers would get us more involved in that.
Okay. Well, that's definitely for anybody watching here, particularly on the kind of the client side, customer side of things. That's definitely one big takeaway.
We would call that exercising our design curiosity.
Yeah, I agree. Yeah, absolutely. That's right. It's it sounds completely logical in the abstract when we're talking about it here, and then it hits the real world, kind of context, and of course that's where the things get a little bit harder to square up and things. In terms of the skill sets and technical backgrounds, I appreciate it's quite a broad question this, and it may be more data focused or whatever. But in terms of application, but impact, are there any things that you, from whatever your perspective is, that kind of go wrong in this particular measurement field? So we're talking about greenhouse gas sensing. Is there anything that people coming into it, perhaps without a lot of practical experience, make a lot of assumptions about and get wrong? Anton, I'll start with you, if I may, on that one.
Yeah, so on the data utilization side, I see there's a lot of data scientists using remote sensing data, which in a way is fantastic. But on the other hand, often they have no idea how the processes work that you lead to those emissions, and it's easy to come to conclusions that cannot be validated. Same thing with the use of AI. We love it, we use it, but if you don't know why AI comes to a conclusion, you can also be led in the wrong way. So I think make sure that people are involved to actually understand the processes, have process knowledge of physics. So I think that's important. On the instrument side, this is very specialized work. So you need experienced people, and there's a big shortage of them. I think I see in my sector across the board that people really struggle to find enough people with the right technical background and experience. It's an issue.
Yeah, it's an issue. It's an issue here. Finding the right technical people to manufacture, test, verify.
Yeah.
Analyze systems analysis. It's very, very difficult. Those are critical things to keeping that timeline short in the development.
Yeah. Is it getting any easier, Tim? Do you see any kind? I mean, it's been a topic that's been talked about quite a lot over the last few years, but
there are some things. There are some things that they're doing here in the States as far as optical manufacturing. We have an aging workforce in optical manufacturing. There are a lot of initiatives to train up new technicians, new engineers in optical sciences, And what's nice is they're getting out of the big universities and into the smaller universities. The smaller what we call our 2-year technical colleges or community colleges, putting in optical fabrication programs, whether it be conventional optics, CNC optical fabrication, or diamond turning fabrication. There's several areas around the United States where all that is being highly accelerated. And that's where we're looking to draw employees from, and we have been drawing employees from.
Okay, that's good to know. And I know there are obviously lots of continental European initiatives around this and things, similar issue. Anton, do you feel it's getting any better on your side of the pond?
Well, I see a lot of good initiatives. So let me be optimistic on that. But it's not easy. We have also indeed in optics manufacturing and design good cooperations with schools, universities, but it requires constant attention. And I think especially if you speak for Europe and the United States, if we want to remain competitive in this, we have to work hard, huh? I think it is not a given that I think Europe and the United States are the leading regions in this field in many ways, but it's not a given it will stay like that. And what I often see, and then I sound really old, but okay, is that we have there's lots of talented young people, but they like to do lots of different things. And for this type of instrument making, you sometimes also need to really, work on it for really a while. And that's tough work sometimes. And to see that as a fun challenge is, I think, something we can sometimes be better at, to show people how gratifying it is to really, for a number of years, dive really into this. And for younger people who live in a world where attention span is very divided over many things, I think it's not such a common thing anymore. So I think maybe we also culturally, if that makes sense, we can help our talented young people a bit.
Okay, no, here to that.
I know over my career, I spent many years developing instrumentation. It's mostly for semiconductors at the time when I was a younger engineer. And what we have some very specific things that we manufacture. We are a world leader in hygroscopic optics. There's not a lot of folks that specialize in hygroscopic optics. So I echo what Anton's talking about, getting people to focus and make improvements and improve salt optics. And how do we make a broadband cesium iodide beam splitter more manufacturable and lower cost. And it takes a lot of attention to detail to take a look at the process and try new things in the process to make those things make yourself more productive. But I spent many years in front of an instrument, aligning and improving and tweaking, and that's a very very focused, to be cliche, a very focused thing that a lot of people aren't looking to do these days.
Yeah, and there's a reason these things are cliches, right? It's because they're based on truth in reality,
But I could be just an old curmudgeon. That's all.
Well, we're all of a certain age, I think, probably. So if you are, we're all in the same space and things. It's fine.
But still, it's still gratifying, and because what I do hear from people who do it, it is you really achieve something at the end of the day, and it's an experience I think I would wish to anybody, because ultimately you do really tangible cool stuff. So it's just not so common anymore anyway. So I'm very optimistic on this, but I think a few changes here and there could help.
Yeah, maybe if the legislators are listening, that's probably a little bit of a cue for them Now, look, this is a perfect segue into kind of what I think should be the start of a bit of a wrap-up section, which is about the future, really. And obviously, photonic technologies have transformed our understanding of the planet, greenhouse gases in particular. I'm wondering what the next big opportunity or advancement looks like. It's quite a big, broad question to sort of end up on. But I mean, Anton, what would be number one on your kind of radar for that kind of issue? What do you think's next?
Oh, that's quite a list. So
that is quite a
let
question.
me start. Let me start with a simple one. So let's assume, and I see that happening, that measurements are increasingly being requested and required, and this market is growing. So I think one of the things is scaling it up. So building robust industrial supply chains for this that can really keep building quality. Also on the remote sensing side. Yeah, and then I see divergence to different wavelengths, different species, different gases to be measured. So more into the thermal infrared, gases like ammonia that cause enormous problems in Europe. If you look at biodiversity due to over-fertilization of soil. VOCs, so cancerous gases. I think these are things that I see in the coming 10, 20 years becoming more important to measure on ground and in remote sensing. But you're diving deeper into the infrared, and that gives all kinds of instrument challenges. Calibration being one of them, instrument size being one of them. So yeah, that would be my take on a fairly general question.
I hear you. And Tim, from your perspective, particularly possibly in terms of some of the work that you're doing at Omega?
Yeah, from our perspective, we're seeing those requests to go further out into the infrared, out into the terahertz. And how do we make components that are going to be reliable and achieve what the scientists want to make out there in the far infrared and even into the terahertz region? And we're seeing that's probably our largest opportunity for new product development and new coding development that we see in our upstream.
Okay, that's
telescope.
Interesting. Okay, great. All right. Well, look, thank you very much to you both. It's always a real pleasure to have such an interesting debate. Anton, you've been terrific. Thank you for your time today. Tim, obviously brilliant to have you on board. Great to have one of our Photonics 100 alumni with us to help lead the debate on this. Tim made the list on the list that we published a few weeks back. So very pleased to be to have you here. Just a final thing to anybody watching live or indeed on demand. So this webcast sits as an on-demand download that will sit on the electro-optics.com website. So if it's been useful, if it's answered some questions or given you some pause for thought, please share that information with your colleagues and get them to have a look as well. It goes without further ado to say thank you very much for watching, everybody. Thank you for your participation. Thank you, Anton. Thank you, Tim. And hope to see you again at another Photonics 100.
One quick question: is my contact information out there if anybody has any questions?
Yes, I was going to say that. So we will put that onto the landing page. So if anybody wants to get in touch with either of our speakers, or indeed, as I mentioned at the beginning, Shankar, then obviously do get in touch with them. We will make sure that all of that information is put on the landing page. But thank you. It's been a terrific debate. I've really enjoyed it. We're going to sign off now. The screen will go dead, Anton, Tim, but that's thanks. But thanks again for your time.
Thank you.
Really good podcast. Take care.
Thank you very much.
Thanks.
Cheers.
Bye-bye.
Bye.
Bye.